Okay, in this video we're going to talk about the rank and the row space of a matrix. So we have a theorem that says that if two matrices are row equivalent, meaning you can row reduce one and make it look like the other one, then they're going to have the same row space, meaning the span of the different rows is going to be the same. So I'm going to just look at a particular example matrix while I talk about this. My row space would be the span of the vectors 1, 2, 3, 2, 1, 1, 1, 0, 1, and 0, 1, 0. So that would be all vectors in R3. And from the previous section, we know that, okay, if there's 4 vectors in R3, then there's no way for them to be linearly independent. So they have to have some linear dependence among them. Anyway, the reason that this theorem works, that if two matrices are row equivalent, then they have the same row space, all of our row operations, like adding a row to another row, isn't going to change the set of linear combinations. So like if I take these bottom two rows, if I doubled the bottom row, we would still have the same linear combination of these two rows. If I added a row to another row, I would still have the same linear combination of those two rows. Okay, let's see. The punchline, though, the way that we're actually going to use this in practice is this corollary, which says that if you can row reduce A, then the non-zero rows are going to form a basis for the row space. So if I give you a matrix and ask you to find a basis for the row space, then we just have to row reduce this. And I'm not going to make you watch me row reduce that. I am going to type it in a calculator, and I think it would be helpful for you to see something that happens there. So I'm going to pull out my calculator, and I hit matrix, edit, and A is already typed in. I'm not sure how well this is going to show up on screen, but A is already in there. It's exactly the same matrix. And so we hit quit, and second matrix, go down to reduced row echelon form, second matrix, A, and if you hit enter, it actually says invalid dimension. So the reason for that is just an error with TI's calculators. You should be able to row reduce this matrix, but the calculator doesn't like matrices that are taller than they are wide. So to fix that, we're just going to put in an extra column of zeros. So instead of being a 4x3 matrix, we'll make it a 4x4. So just a phantom column of zeros showing up. And then we do the same thing, row reduce A, and it should give us this matrix. And again, we have a phantom column of zeros. We can just ignore that. So we have 3 ones on the diagonal and zeros elsewhere. So our row reduced version of A is going to be 1 0 0 0 1 0 0 0 1 0 0 0. Okay, so a basis for the row space the weak hat. A basis for the row space is these non-zero rows, the top 3 rows, 1 0 0, 0 1 0, and 0 0 1. So those 3 rows. Okay, the rank is the dimension of the row space. And so it's the number of non-zero rows, which would be 3. So you can either think about it as a dimension of the row space, or you can think about it as the number of non-zero rows after row reducing. Okay, let's try another one. Here's a matrix B. Again, I'm going to type this in a calculator and get the reduced row echelon form. This one is wider than it is tall, so I shouldn't have any problems with row reducing this one. So I'm going to pause the video real quick and write down the row reduced version. Okay, so our row reduced version of B is this matrix, which has 2 non-zero rows. So those 2 rows are going to be my basis of the row space. So 1 0 2 negative 1 3 as a vector, and 0 1 minus 2 2 1 as a vector. Just make sure you are actually including any zeros that are showing up in there, because we don't want this to be like a vector in R5 and a vector in R4. That wouldn't really make sense. And so our rank is the number of non-zero rows after row reducing, or it's the number of vectors in your basis, which would be 2. Okay, something to point out while we still have this on the screen. The basis of the row space is these two. That means everything in the row space is a linear combination of these two. So in particular, every row is a linear combination of these two. And so if you stared at it or wanted to actually solve for the constants, we could actually figure out how to write the first row as a linear combination of these two, and how to write the second one as a linear combination of these two. I think the first one is actually going to be 1 times the first plus 2 times the second, if you wanted to write this as a linear combination of those two.